cylinder with these dimensions will have a cap end area of approximately 7.07 square inches, a rod area of approximately 1.23 square inches, a rod end area of approximately 5.84 square inches, a cap end volume of approximately 113.1 cubic inches, a rod volume of approximately 19.6 cubic inches, and a rod end volume of approximately 93.5 cubic inches. Additionally, a flow rate of 1.8 gallons per minute is equivalent to 415.3 cubic inches per minute. All of these calculations will remain true regardless of which mode the cylinder is in, normal or regenerative extension. There is no need to calculate these values twice. In normal extension mode, pressure acts on the full cap end face and the rod end is dumped to tank. Pascal's law states the maximum extension force in normal extension mode is therefore 3,534.3 pounds force. In normal extension mode, flow must fill the fully cylindrical cap end volume. Flow rate calculations suggest that this will take approximately 0.272 minutes, or approximately 16.3 seconds. In regenerative extension mode, pressure acts on both the full cap and ring-like rod end, resulting such that only the area of the rod favors extension. Pascal's law states the maximum extension force in regenerative extension mode is therefore approximately 613.6 pounds force. In regenerative extension mode, outgoing flow from the tubular rod end volume is routed back into the cap end. Flow must therefore fill the smaller volume of the rod only. Flow rate calculations suggest that this will take approximately 0.047 minutes, or approximately 2.8 seconds. Again, note that while comparatively weaker than normal extension, regenerative extension occurs much faster. Applications for regenerative extension are numerous. A classic application example being an industrial process that must move something rapidly into position prior to doing any work necessitating substantial force. Consider a cylinder with a 24-inch travel length being used to split 16-inch logs into firewood. The first 8 inches of travel is wasteful since the only purpose is to move the wedge into position. Once the wedge makes contact with the wood is the only time work is really being performed. It makes sense then that the first 8 inches of travel should occur as quickly as possible. For this reason, the first 8 inches of travel is performed in regenerative extension mode. Force exerted is lower, however extension speed is much faster. Once the wedge makes contact, the cylinder is switched to normal extension mode, where extension is slower, however, force exerted is much greater. A cylinder operated in this manner saves the operator the wasteful time of moving the wedge into position using regenerative extension, yet is still capable of exerting substantial force using normal extension. Just the opposite method can be used for an entirely different application. Consider an industrial process that necessitates a substantial initial force to break static inertia. However, once an object is rolling, the act must occur as quickly as possible. Consider a hydraulic cylinder used to pitch the blade of a modern horizontal axis wind turbine generator. In the event of an emergency shutdown, the cylinder can be used to change the angle of attack on the blade and safely aerodynamically brake the rotor. When an emergency shutdown is initiated, the cylinder can act in normal extension mode to exert full force. However, once the static inertia of the heavy blade has been broken, the cylinder can be switched into regenerative extension mode to keep it rolling as quickly as possible. A cylinder operated in this manner allows an initial burst of force in normal extension mode, yet it is still capable of acting quickly in regenerative extension mode. Another cunning regenerative application is something known as a 2-to-1 cylinder, where the physical dimensions of a 2-to-1 cylinder are such that the cap has twice the area of the rod. 2-to-1 cylinders are designed to be operated with a special type of directional control valve with a regen position that routes pressurized flow to both cap and rod end, serving to extend the cylinder, and a cross-connect position serving to retract the cylinder. The mathematically astute among you realize a cylinder with these dimensions and operated with this type of directional control valve will exhibit a unique characteristic, that of equal extension and retraction force and equal extension and retraction speed. Ordinarily, a double-acting cylinder in normal extension mode will always exert more force at extension than at retraction, due to the area imbalance between cap and rod end, and will always retract quicker than it extends, given the volume imbalance between the cap and rod end. For a 2-to-1 cylinder operated with this type of directional control valve, these constraints and complications are a thing of the past. By all means, pause the lecture and prove it to yourself. Calculate the maximum force of extension and the maximum force of retraction, and the time to fully extend and fully retract this cylinder, given this system is limited to, let's say, 700 psi, and flow rate is 0.9 gallons per minute. Here's a hint. Extension and retraction force should be equal because the rod area equals the rod end area. Additionally, extension and retraction time should be equal because the rod volume equals the rod end volume. Finally, many different types of regenerative circuits exist, all more cunning than the next. I'll try to illustrate just a couple simple ones here. Consider a special purpose, manually actuated 3-position directional control valve that is spring offset into the cross-connect position. Ordinarily, 3-position directional control valves aren't spring offset, but rather spring centered. In this case, however, when an operator isn't touching the manual lever, the directional control valve is pushed into the cross-connect position and the cylinder fully retracts. When an operator moves the lever to the soft stop, the valve moves into the center regen position and the cylinder extends rapidly, yet weakly in regenerative extension mode. Finally, when an operator pushes the manual lever past the soft stop into the hard stop region, the valve moves into the far left straight through position and the cylinder extends slowly, yet strongly in normal extension mode. When an operator releases the manual lever, the cylinder fully retracts. Such a valve is a perfect fit for a log splitting application. Hit the manual lever once, it extends the wedge quickly, but weakly. When the wedge makes contact, push the lever past the soft stop and it splits the log strongly, but slowly. Such a system uses a single-stage pump and is characterized by 2 modes, high speed and high force. We'll discuss something called a high-low pumping scheme, making use of 2 pumps and a pressure control valve known as an unloading valve that largely accomplishes the same purpose in later lectures. The advantages of regenerative extension over the high-low method should be obvious. You only need 1 pump. In the interest of full disclosure, I did not have a log splitter growing up. If splitting logs with an axe and stacking them in the dark, in the cold is a character building exercise, trust me, I am full of character. Absolutely full. Here's yet another directional control valve with regenerative possibilities. The schematic symbol is a little busy, but if you take your time, you should be able to figure out what is going on. First, this is obviously a manually actuated valve. It has 4 positions and features a mechanical detent. Internally, it has 5 ways. Note the enclosure symbol also includes an integrated pressure relief valve. Basically, all you need for this valve is a hydraulic power unit and a cylinder, and you've got yourself a complete system. If P and T are respectively connected to the pump and tank, and actuator ports A and B are respectively connected to the cap and rod end, see if you can determine how the various positions function. Note when the valve is spring offset into its deactivated position, pump outflow is routed to tank at low pressure, thereby keeping the main pressure relief valve closed. Additionally, note actuator port A is at low tank pressure, although actuator port B is blocked. This is quasi-equivalent to a tandem position. When the manual lever is moved into the soft stop position, this is equivalent to a straight-through position that routes pressurized flow to the cap end of the cylinder and dumps the rod end to the tank for normal extension. This is the high force position. The hard stop position is equivalent to a regen position that routes pressurized flow to both the cap and rod end for regenerative extension. This is the high speed position. Finally, when the manual lever is moved in the opposite direction, the valve shifts into a cross-connect position that retracts the cylinder. The valve also features a pressure-released mechanical detent upon retraction. When the cylinder fully retracts and pressure rises to the adjustable kick-out pressure, the detent automatically releases the valve to the deactivated spring offset tandem position, again keeping the main pressure relief valve closed. You note that the 5 internal ways are kind of confusing, since the valve can be more recognizably depicted as one with 4 ports, but hey, There is no law saying that you have to be consistent and understandable. Finally, other types of regen circuits you may run across are ones that do not make use of special purpose directional control valves with fancy regen positions, but rather regular directional control valves or perhaps pilot operated check valves. This example selective regenerative extension circuit features two additional directional control valves, a normally closed directional control valve A between the cap and rod end, and a normally open directional control valve B on the rod end of a cylinder. When these two valves are in their deactivated state, the cylinder extends and retracts as normally. However, when they are in their activated state, directional control valve A opens and directional control valve B closes. And the main directional control valve is shifted into the straight-through position, the circuit operates in regenerative extension mode. Note, while these solenoids are energized, moving the main directional control valve into the cross-connect position would not retract the cylinder, but rather allow the cylinder to float freely. These additional solenoid-actuated directional control valves, therefore, are mode selectors. When deactivated, the system is in normal mode. When activated, the system is in regenerative extension mode. Alright, that is about that. Before we close up shop, allow me to crush your dreams. No, there is no such thing as regenerative retraction. I know some of you are already scheming of cunning ways to create and patent a regenerative retraction device, but good luck doing so, since the volume differential inherent in a regular double-acting cylinder only makes this method work during extension. Yes, you can put all sorts of crazy secondary components like intensifiers and accumulators and more directional control valves and pilot-operated check valves to kludge together something that kind of does the same thing, but my response to all this silliness is why? The principal attraction of regenerative extension circuits is their simplicity, often necessitating just a special purpose directional control valve, a couple directional control valves, or even some pilot-operated check valves to make it work. We'll examine high-low pumping circuits in later lectures, making use of two pumps and a pressure control valve known as an unloading valve that exhibits not only increased extension speed, but also increased retraction speed. However, does so at the cost of slightly more hardware. In conclusion, this lecture introduced regenerative extension circuits. We learned that a double-acting cylinder will always extend when equal pressure is applied to both the cap and rod end because of the fundamental functional area imbalance. Additionally, we learned that while extension force is weaker in regenerative extension mode, extension speed is significantly faster. Finally, we discussed basic applications of regenerative extension and examined a couple representative circuits that made regenerative extension possible. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.